So hi everyone, today I'm going to talk about our recent work on adaptive online learning of quantum states. And this is a joint work with Xinyi Chen, Ilan Hazan, Zhou Lu, Xinzhao Wang, and Ray Yang. And if you're interested, you can find our paper on arXiv here. So in general, this work is about algorithms in quantum computing. So maybe let's talk about first the high-level picture here. So in general, why should we care about quantum computing? I guess there are multiple reasons, and actually there are many different perspectives. But I think probably one of the most important thing is that on quantum computers, we can get fast algorithms for classically hard problems. So for instance, at the very beginning, I think this is really like the origination of quantum computing. In the 1980s, Professor Richard Feynman actually think about like the simulation of quantum systems, which is a very different, actually a very difficult problem in general. But maybe we can actually, hopefully we can utilize the computing power of quantum mechanics per se, so-called a quantum computer, to simulate the evolution of quantum systems. And actually, hopefully this can be done in the future. So this is really a great prediction by Professor Richard Feynman. And later on, along like the computing side, and actually there are some famous algorithms along this. So for instance, a very important algorithm is the Grover's algorithm for searching. So basically, if you have a database, and for instance, if the database has size n, and you want to search for a specific item inside that. So classically, this is really, I mean, in the worst case, you probably just have to look everything brute force, and the cost is going to be a linear in n. But quantumly, the cost can be, roughly speaking, making into like square root of n. So this quadratic speedup is very important. Just like the search is such like a fundamental problem, and also such kind of a quadratic quantum speedup has wide applications in all kinds of algorithms. So moreover, a very important algorithm, actually probably one of the most important algorithms in quantum computing, is the shortest integer factorization algorithms. So this is actually a very important thing in classical cryptography, that you just have two large primes and you multiply them together. So if I just tell you this large number here, it is in general very difficult to factorize it into this. But actually on quantum computers, the shortest algorithm can solve the factorization problem with high success probability only in polynomial time. So this makes a huge difference actually in cryptography and also a lot of related areas. And actually this actually one of the milestone that brings people attention to the study of quantum computing. So since then, I mean, after like the idea of quantum simulation and the important algorithms such as the Grover's algorithm and the Shor's algorithm, there has been gradually more and more studies on these lines. So for instance, people have been talking about quantum algorithm for solving linear systems, for graph problems, maybe also for some Boolean functions like formula evaluation, and also for some abstract algebra problems, for instance, like decomposing groups, etc. So these are actually a lot of problems that quantum computers can really do a much better job compared to the classical counterpart. But actually, a very important thing that I think, at least from my perspective, is that current quantum algorithm research, as you can probably see, that from a computing side, that we have been talking about like the search problem, like the factorization problem. And actually, a lot of these kind of problems, I mean, like Boolean integer domains. And actually, even for some very basic questions, I mean, in the continuous domain, I think especially, for instance, in optimization, continuous optimization, and machine learning, etc. I think a lot of questions are still widely open these days. So people should really probably have made more efforts on this line to actually have a better understanding about like the power of quantum algorithms into these kind of problems. So from a high-level perspective, my personal research is actually to trying to bridge the gap between quantum computing, optimization, and machine learning. I have to say that mostly, I mean, I have been doing this along like a theoretical perspective. So in particular, I mean, by bridging the gap between quantum computing and optimization and machine learning, I basically want to have a good understanding about like, what is the quantum speedups of optimization and machine learning? So basically, if we can, if we want to solve this kind of problems on quantum computers, what are the advantages that we can share? So this actually basically like we just like shift this from like the Grover's algorithm and Shor's algorithm, like the quantum advantages from the discrete domain to continuous domains. And in general, maybe we can talk about different kinds of problems. So for instance, we can talk about like the quantum speedup for unstructured problems, where in general, we just like have some, for instance, like general function evaluations. Along this, we can actually give some fast quantum algorithm for solving a general convex optimization problem, or maybe related problem of estimate the volume of convex bodies. And actually, this can be further extended to some non-convex problems. So, for instance, about the problem escaping from saddle points and beyond. So we basically have demonstrated the quantum advantage for such kind of problems. And also for some related problem where we have some data stored as matrices. So there are also some other kind of things that like maybe some of the words are familiar with, for instance, like the semi-definite programs, like the classification problems, like the matrix game, and also very importantly, like the quantum-inspired classical algorithms. So basically, we can give, like, theoretically speaking, give fast quantum algorithm for such kind of things, and also related quantum-inspired classical algorithms. So this is just like a very high-level sketch about what I've been doing. But I think since the focus of this series is about like quantum computer systems, I think in general maybe most of the audiences here are more interested in like the practical side. So also actually a question asked, I think, not only to this lecture series, but also to myself is that how can quantum algorithm research be relevant in near term? So I think these algorithms, I mean, like the Grover's algorithm, like the Shor's algorithm, and I think my theoretical research, I mean, these results, I think they're actually, from my perspective, very interesting. But I think, I mean, as a researcher currently in quantum computing, and I think as the field is really evolving fast. And I think we should really probably also make efforts to this improvement really in the near term, and hopefully we can give some good results along this line. So I think as I have really been devoted into like the theory research here, and I think from my personal perspective, I also want to like make gradually try to hopefully my expertise can give like a good investment in terms of making everything more practical. So I think my personal take on this is that I want to study quantum algorithm for practical problems. So, I mean, there are a lot of practical problems, but basically the focus of today is that we want to talk about the important problem of third quantum states. So this is really fundamental because quantum state is like one of the most basic components in quantum computing. In general, I mean, I think for learning quantum states, I mean, machine learning and like existing results can really play a major role. So this is actually the angle that I'm actually cutting into this. Okay, so let's delve into this, and for the talk today, let's talk about the problem of learning quantum states. So what do I mean by that? So maybe we want to be a little more precise on this. So in real world experiments, I mean quantum experiments, it is common that we have the capability of generating copies of a quantum state rho. But what is the state? So for instance, if we are preparing for a specific state, is the prepared state close to our goal? So I think this really happens, I mean, for instance, in the calibration of current quantum devices, that maybe you are very excited that you have a quantum chip with like dozens of qubits and you run a quantum circuit along this. But we all know that currently quantum computers, I mean, like the 1 qubit and qubit errors, they are always such kind of things. And maybe the state you prepared is not exactly what you want. So in this kind of thing, in this kind of cases, we really want to be careful, and we want to make some calibration, and we want to make sure that we are preparing the right state that we want. So a theoretical problem along this, a very important problem, is called quantum state tomography. That using how many copies of like a d-dimensional density matrix rho are necessary to output a certain state. I mean, we call it like a rho prime, such that it is very close to the original state that we can actually take in samples from. So this problem of the quantum state tomography is one of the most basic problem, and actually this has been widely studied and in seminal works due to Ha and and also Donald Wright, both in 2016. It is proven that for the quantum state tomography problem, the sample complexity is basically d squared over epsilon squared up to polylogarithmic factors. So we want to be careful here because the d here we are talking about is basically the dimension of the state. So if we have n qubit quantum state, so basically because it is like a density matrix here, so this basically gives like a factor of 2 to the n squared, which is 2 to the 2n, and this is just intractable in general. I think currently in like by experimental physicists, like the largest number that people can do such kind of quantum state tomography is roughly speaking like 10 qubits or maybe 12 qubits or something like that. So in general, this problem of quantum state tomography, it is super important. But I have to say that this is probably something not very practical for now, and maybe we have to think about some alternative goal that can actually facilitate this. So I think specifically a very important alternative goal is basically the problem called shadow tomography. So for this problem, we make the relaxation such that we don't want to have like we prepare like a state rho prime here that is really close. I mean, for instance, like trace error epsilon to the original state. But maybe we are okay such that we have like a group of measurement operators, E1 to EM. We are happy enough such that we can prepare a state rho prime with the fact that the trace of the rho prime times the measurement operator EI for all of the I's here are epsilon close to the true value. I mean, the trace of rho times EI for all of the I here. So this shadow tomography problem is actually originally proposed by Scott Aronson, and there has been a lot of subsequent works on this line. I think as far as I know, the state of the art was due to Badescu and O'Donnell last year. So basically using, roughly speaking, like log m squared times log d or epsilon to the fourth power, we can actually achieve the goal of the shadow tomography. So the m here is the number of POVM operators here, and the d here is the dimension of the density matrix, and epsilon is the epsilon of the trace here. So you'll see this result is actually quite good, that basically we achieve like exponential improvement in terms of d here, the dimension of the density matrix. So, but I think still there are different concerns, and I think especially in practice, there may be some thoughts along this line. So for instance, like the shadow tomography algorithm, they actually require a joint measurement on the copies of the state rho here. So this like originally proposed algorithm due to Scott Aronson, and also the follow-up works, I mean, also including the state of art due to Badescu and O'Donnell. So basically they require that we have like all the copies of the rho. I mean, these number of copies of the state rho here together, and we make a joint measurement, etc. This, I mean, this is, I mean, the number of copies here is not that large, but like a joint measurement maybe still a little bit restrictive, I think, from the current perspective of basically the current capability of quantum computers. And also the second thing is that in general, the measurement operators, yeah, can be given sequentially. It is not, I mean, in this original statement of the shadow tomography problem, we just give this set of measurement operators to you. But I mean, the people's goal can change in general. I mean, we want to have like it is probably after we make this group of measurements, and maybe we want to have like a further group of measurement operators, and we want to give a good prominence upon. So this is really something that somehow is like online, and it's really not directly in the feature of this kind of shadow tomography problems. And I think a very important thing that I'm actually going to focus on today is actually we want to make this even more practical. That basically quantum states have fluctuations, because I think typically it is not that common that we have like really like a good quantum circuit that can always prepare the same state rho here. I think this would be fantastic, but actually in real cases, that quantum states have fluctuations and can change over time. So this is something that we should really be careful about. And maybe, and I think as a summary, I mean, also in light of the previous literature, I think a very important paper due to Aronson and Chen, Haza and Kali and Naya, they actually have studied the first 2 points by basically utilizing the classical learning side, basically online learning, to use online learning techniques to study quantum states. And this is a really nice result. And actually our work is built upon that. But I think for the main topic of today is that we really want to look for something that we can deal with quantum state having fluctuations. In terms of machine learning, a very standard term here is called adaptivity, and we are actually also correspondingly using the techniques along this line. Okay, so this is like a high-level picture along this, and maybe let's delve into the topic. So for our results on adaptive online learning of quantum states, so maybe let's first make the definition here that we consider such kind of n-qubit density matrices. So basically, this is like a very standard definition here. And I think in terms of online learning, that something we are going to borrow here is a standard definition is the regret. So basically, we want to make sure that we have like maybe, for instance, like the state given you and also the measurement operators given you one by one. How do we measure whether we are given like a good prediction or not? So we are going to like construct like basically we consider everything cumulatively that we define such kind of regret. And basically, this thing is that what we actually predicted along the procedure of learning. And actually, there are maybe for the static case, there are some background state phi here, and actually we want to try to minimize such kind of summation along all these number of rounds. And so here the LT here is the loss function that we are going to use throughout the talk, and maybe and I think there are many different choices. And I think here we can in general think about something that maybe is like the trace distance, and maybe it's probably also like its corresponding L2 norm version. And here I think in general we make the prediction that the loss functions are L-Lipschitz functions. And I think this is probably basically the only thing that we are going to use. So in light of this, I think it is probably the right time to carry out the definition of dynamic regret. So as you can see, the definition of dynamic regret is actually quite similar to the definition of like original regret, I mean the standard online learning scenario. Whereas the only relaxation is that in terms of making the comparison to the best possible like regret, I mean there's comparator here. We now consider like the case where we can alternate, I mean we can change the state here, the phi t here. I mean, but of course we cannot like arbitrarily change the state, because that will make the problem too difficult. So we just consider like another variant here, which is called the p. And actually it is going to be the summation of the difference between like the consecutive changes, like the difference between the phi t and minus phi t plus 1. So this might look a little bit strange because there's like a star in this norm. So this thing is called the nuclear norm. And the nuclear norm is basically, if you have a matrix here, it is the L1 norm of the singular values. And the P here for our definition, and I guess intuitively you can imagine this is like a hand of like the changing of the states. And this is typically by a standard term called the path length. So this is basically the first definition of the dynamic regret. And I think following that, another very common situation that people also study is that maybe we want to consider a case that we know that the change can only happen from like a certain set. For instance, we only have like some possible dynamical models, and each of which is being a quantum channel. So such kind of things also happen commonly. So for instance, maybe we can consider a case where the quantum channel is basically this like evolution of the Schrödinger's equation, where we have like a background Hamiltonian. So why do we want to say such kind of thing? So for instance, we can just imagine that in current quantum devices, for instance, like the Sycamore device in Google. So basically, this is like fabricated in a 2D dimensional way. That basically we can only have a quantum gaze in consecutive qubit pairs. So basically, this really gives you like a restricted model of Hamiltonians. But maybe, for instance, maybe you don't know exactly what the coupling between the consecutive pairs of qubits. So in that case, we know that there are some certain settings of the dynamical models, although the values you don't know, but basically you know that this is probably a set that we're going to get restriction. So in this case, we can give also correspondingly a similar definition of the path length. And actually, the definition is going to be the minimum of this kind of summation. Actually, it's somehow similar, but actually this thing is going to be like the phi of the capital phi of the phi t here, where the capital phi is one of the quantum channels that can take place here. Okay, so by giving the definition here, I guess it is probably the right time to carry out the results along the dynamic regret. So the first result is that for the path length setting, we can give a quantum algorithm that can achieve the result, roughly speaking, like square root of t times p here. So the t here is the total number of iterations, and the p is the path length that we just described. So the second result is also for the dynamical model setting here, we can also give a similar results that basically the cost is still also like a square root of t times the variant of the path length p prime. And I think maybe, for instance, like a direct corollary along this line is that maybe, for instance, with dynamical models such as like L local quantum channels, such that basically the dynamics can only influence at most L qubits in the case. Actually, in this case, we can give a regret result that is basically this kind of square root of t times the p prime, and also for the for the locality, that basically the number of qubits that the quantum channel can influence is basically like 2 to the 6 times L. But I think basically in general, for instance, like if we were maybe for the 2D case that we only each time we can influence like 2 qubits. So this L is just like 2, or maybe in many cases it's just a constant. So this in general is not a big problem into this result. So these are our results for the dynamic regret. And I think as the title suggests, I think there are always some like adaptivity, and I think there are some natural definition along this, also called adaptive regret. So along this, I think it is typically defined in the sense that maybe we normally have good regrets in like finally, I mean, in the round t here cumulatively. But actually, by adaptivity here is that maybe along this kind of way, you always have a good prediction about what you're actually having. And to actually characterize this, the way that we are going to make is that we want to make sure that along all the intervals, I mean, intervals of a certain length here, we are always making a good prediction. So for instance, like the standard regret is just like taking the tau here equals to 1. So by doing that, we actually can give a result for the adaptive regret, and basically we can also basically give such kind of result in terms of the adaptive regret. And also, I think to basically carry out this, it's probably a little bit something abstract. I think we want to be a little bit more focused about like the dynamics that can take place maybe in real case. So here we consider the setting where we have like a K shift. By that, maybe we want to allow some changes to the state, and this change can be something arbitrary, but we are promised that the change can be at most take place like K times. So by doing that, you can see like this regret is really probably something natural that we want to consider minimization along all the intervals, such that basically maybe like some state is arbitrarily happening here, but it's actually changing for at most K times, and basically we want to make comparison to such kind of regret. And actually we can give a good regret down for this. And I guess maybe what I'm saying here is too abstract, but let me actually summarize everything into a table like this. So basically in our result that we use this kind of online learning techniques that can give good characterization, that basically for the dynamical model case, and also for the path length case, and also for the K-shift case, we can give a good corresponding quantum algorithm with regret, basically always like square root of t. I mean, if this like in general, like t iterations, if you have like overall regret of square root of t, this is small. I mean, the average regret tends to 0 in general. And basically, the square root of t is probably something best we can hoping for, because in a lot of online learning literature, the square root of t is actually the lower bound. So I guess probably is the time for me to make a pause here, because I actually like I have introduced the main results here and actually the problem setting. So maybe if you have any questions about the setting regret, just feel free to ask. Okay, so I guess when I'm introducing, you can just always feel free to interrupt me and ask any questions. So I think this is probably just like the setting, basically the definitions about how we are actually using online learning tools to study such kind of learning quantum state problem, and actually our result in different kinds of models. So I think due to the limitation of time, I'm probably not going to introduce like the techniques or the detailed techniques, but I think maybe I can still give you some intuitions along this line. So for doing that, I think a very standard technique in online learning is called the follow the leader. So what do I mean by that? So maybe in general, let's just consider like a standard online learning problem like this. The most straightforward approach is to use like anytime the optimal decision. I mean, you have the knowledge of the previous like predictions and outcomes, and basically these loss functions. So basically, each time, I guess, like a very like straightforward thing is that you have all these kind of loss functions. You just like plus them together and like choose the arc mean of as the prediction of your guess. I guess this is something that you can really think about. And I think in economics, this is typically called a fictitious play and has been named as the follow the leader in machine learning. So, however, I think there are some issues with this. And maybe let's take a look at a very simple example. So maybe let's take a look at this. So we have like a one-dimensional problem where the definition domain can be something like between -1 and 1. And the functions is that maybe, for instance, at the beginning is like -0.5x, and then after that is like alternate between plus x and minus x, minus x, x minus x, etc. So you can see the issue with this kind of follow the leader in like a really straightforward way. So maybe, for instance, I mean, at the second round. So at the second round, you ought to make a prediction of what you're going to choose for x2 here. So for x2 here, I mean, at this time, you only have the knowledge of the first function. Oh, you see the first function is -0.5x. You just like choose the minimum. So if you like look at this and look at the definition domain, of course, the minimum that you can choose is you just like take x2 to be 1, and this smallest value can be just like -0.5. So this is the value of x2 you predict, but unfortunately, this is really a bad prediction because at the value of x2, and you're actually making a regret here, you like sum the function f1 and f2 here, and actually their summation is plus 0.5x, and actually you are making the really the very bad prediction. And actually for x3 here, if you just like make like a prediction based on what you have seen, like you have seen the function f1, f2 here, and I guess f1 plus f2, okay, it is like positive 0.5x. And you guess maybe you want to make it to be like the like you want to make a minimal value, and you just like choose the x here to be -1. But unfortunately, you really made a very bad prediction again, because actually the summation of f1 plus f2 and f3, it becomes like -0.5x, and actually the minimum value takes place at x equals to positive. So you see like the issue with this. I mean, this is like the tricky thing of online learning, that it is probably not necessarily at each time you are making the optimal decision at the time can give you the best thing. And actually in this kind of strategy, the regret is actually omega of t. This is really not something very helpful. So, but nevertheless, I guess intuition, I mean, we always want to make the online learning result good. This intuition of like making some optimal decision is correct. But actually, you see like this kind of thing. I mean, this is really not something, I mean, intrinsically, it makes sense. But what actually influences the problem is the stability. I mean, because this function just oscillates too fast. I mean, your prediction is just like getting behind this. So this is not something very good. And maybe, I guess, adding some stability can really help you along this. So this is actually something standard in online learning, and this is typically, I mean, follow the leader if it's not good enough. We follow the like a regularized leader, and this is typically called the RFTL here, regularized follow the leader. So by doing that, I mean, we just add a regularizer here. So after adding the regularizer, we then take the minimum, and actually this just magically works in a lot of real cases, and especially, I mean, we are going to combine it because we need to train the parameters, and this actually comes from gradient descent. So this regularized follow the leader along the way of the gradient descent methods. So this actually leaves the gradient descent to a standard term called a mirror descent. So this is probably, I guess this is just intuition. Maybe let me not open the technical details. But if we want to have like a TLDR, I mean, too long don't read. I mean, one sentence summary about our techniques is just that we use the online version of the mirror descent, and actually the regularizer that we use is the von Neumann entropy being the regularizer. So in particular, if for instance we take a look at our algorithm here, so this is the algorithm that we use in our paper. So you can see that basically we have inputs, and this basically by von Neumann entropy, you see that the Rx is basically what we choose here. So we have the initialized setting to be the standard, like just the identity matrix, and we have like a for loop that basically this is the thing that we are actually making the regularized follow the leader. So let me also give you some annotations here. So maybe let's delve into a little bit more details. So the line 1 here, you see there are some a little bit shift here. I mean, it is not like the original CN, like the site of the set of like incubate quantum density matrices. So we want to make a little bit shift because the von Neumann entropy, we want to talk about the logarithm here. So especially after gradient here, we have like identity plus log x. So this, if we we are not careful enough, if it goes to 0, this is really going to give you something unbounded, and this is not something we really want. So we make a small like a shift here to the problem to make sure that we have an upper bound for the Bregman divergence. So the Bregman divergence is basically it's like a somehow like a information measure between this kind of like X and basically what you predict. It basically follows along this way of making this kind of von Neumann entropy. So basically, we want to make everything bounded and making a shift. And because this shift is not large, and actually it's like a tiny shift with this kind of thing, it is not going to influence the final complexity of our algorithm. And actually, as I just mentioned in line 2, a very important thing is that we not like naively follow the leader, but we make the regularization using the von Neumann entropy. So for the 5th line here is basically where we make the prediction, because we are talking about online algorithm. We always got to make a prediction about, like, for instance, what is the quantum state you are learning. And this is basically the step we are actually making a prediction. And then we have this loss. And actually, after having the loss, we are, of course, going to make some adjustment. I mean, by adjustment, it's just like we run this kind of mirror descent, and basically we run this kind of things, and basically we give our output, and actually using this kind of updates in our online learning procedure. So this is very roughly speaking like an intuition along this. And maybe like a remain question here is that we want to be a little bit careful, is that because this is in general like a gradient descent, I mean like a mirror descent problem, but we don't know the step size. We actually, in this algorithm too here, we just treat the step size here as given. But this is not something we can actually directly given to. And basically, in terms of giving a good learner for this online learning of quantum state problem in general, we actually have to also deal with that. And there are actually really going into some technical details here. But I think roughly speaking, the idea here is that we actually also need to deal with the thing that we don't have the knowledge about what the path length is. And actually, in general, we need to have like a flexibility about what the learning rate is. And actually, we achieve this by instantiating copies of the online mirror descent algorithm with like different learning rates and experts. And basically, we just compete between different experts. And actually, we update the corresponding weight. Basically, these experts use the multiplicative weight idea to select the best expert. So what do we mean by that? So we just like set a group of like a learning rates, maybe like beginning it's like a half, like a quarter, etc. So basically we consider like the learning rates to be like 2 to the minus this kind of things, and we just like run our algorithm to along this. Like we use this learning rates as our guess, but we are going to make some competition here, because maybe if your learning rate is not appropriate, this really gives you some bad results. So we actually basically you can see the final prediction that we are going to use is actually like a weighted version that actually the weight is going to be updated in such kind of exponential way. So why do we actually have this kind of things? This is actually the way here we want to make this kind of thing, that if we have like a loss that actually, for instance, you have a learning rate that gives you a small loss, and this actually gives you a larger rate. But if the loss is not so good, then this is probably going to give you like a smaller rate. So this, in general, this kind of strategy that you have like a weighted version, because if you don't know the learning rate, you have such kind of weighted version, you compete and you update this in like exponential way. This is actually something standard in online learning, and this is typically called a multiplicative weight. And this kind of updates in an exponential way is also, there are some approval guarantee along this to make sure everything is working on well. So actually, in our final algorithm, we just like combine these two together. That the algorithm one is like the main algorithm. We're actually, after having like a guess of the learning rate, we just run this kind of online mirror descent for the like learning quantum state problem. Okay, so how about like the technical contributions here? So we need to make some comparisons, because I mean you can imagine that, for instance, like both on the classical side of online learning and also on like the quantum side about like quantum state tomography, about like learning quantum state, like due to this all the measurements, I guess this are just like a vast majority literature have actually have carefully investigated such kind of problems. So in general, we want to be a little bit careful. So for instance, about like the comparison to like classical state of art online learning algorithm, I guess the main contribution here is that, I mean, we really want to be careful with the dimension. So actually, I mean, this is just like a way we apply classical online learning techniques to quantum problems. But if we are not careful, the dimension dependence easily have a factor of 2 to the n, plus like the density matrix have such kind of dimension. So this is really something we don't want, and this is actually after looking into the techniques, a specific reason that we want to choose this kind of online mirror descent using Von-Neumann entropy as a regularizer. And also, I think a very important thing, I mean, compared to, for instance, the NeurIPS 18 paper, Online Learning of Quantum States, I think our framework really can be adapted to the case where the states are changing. And actually, we basically use this kind of OMD plus MW, and actually really works well with the dynamic regret case. But actually, there are some really also some technical contributions. Not like we have something in online learning, have something in our understanding of shadow tomography, concept tomography, just glue them together. So there are something we really need to polish through along this, and there are some specific kind of theorems and results that we need to clarify. But roughly speaking, it's like this, like a generalized Pythagorean theorem, and also like basically we need to make sure that the analysis of the Brakman divergence also go through in terms of complex variables. And also we have to using something from quantum information theory to find the difference between the Von-Neumann entropy between two quantum states. So there are basically some technical contributions that is also given in our paper. Okay, so this is basically our result, actually how we achieve this. And I think this is basically what we have been doing for the dynamic regret case. So for the adaptive regret case, the basically high-level strategy is the same. Though we use another different gadget, which is called coin betting for changing environment. The CBCE algorithm is actually a very good classical paper along the way of adaptive online learning. So we use this and plus our OMD using the regularized follow the leader, and we gave a good algorithm also for the adaptive case, which covers like the K-shift case in general. Okay, so this is basically our technical results, and maybe I think like the one last thing about our technical contribution here is that we want to talk about something called a mistake bound. So I think I've been talking about like online learning, like regret. I mean, these are somehow it's like a jargon in machine learning, and maybe you want some like more intuitive way to see this. I guess a very intuitive way to see this is the mistake bound. So for instance, like in the path-length setting, I mean, it's like as just mentioned, we have like a sequence of two outcome measurement operators, it's E1, E2, etc., and also the states. And because by making this kind of prediction, each time we are going to actually give you a value BT here. And actually, we can see like an even more robust version that, I mean, the true answer to this is even not necessarily like a precise one. It's as long as you give me like a value of BTs that is like epsilon over 3 close to the true value, I mean, we are good. So using such kind of, I mean, the measurement operators, and like each time after you make a prediction, you actually get the value of BT here. Then there is actually an explicit strategy, I mean, explicit quantum algorithm such that you can output some hypotheses, I mean, X1, X2, etc., so that basically your prediction is probably deviated by at least epsilon, I mean, this by epsilon. This does not happen for many times. That basically happens for like L squared times N times P or epsilon squared times. So this is just like we have like a hard promise about like what is the number of mistakes that we are going to make throughout our algorithm. And similarly for the K-shift setting, we are actually also giving the prediction that as long as your state can change, I mean, even change arbitrarily, but for at most K times, you can give a quantum algorithm that actually our mistakes, the number of mistakes made is at most like K times N or epsilon squared times like a log factor. So these are like the technical results, and I think as a conclusion of this, I think because we really want to make everything practical. I mean, I have to say that probably, I mean, the algorithm I'm talking about is probably not as practical as like other algorithms talked about during this very nice series. But I think nevertheless, we actually make efforts along this that we demonstrate numerical experiments for our quantum algorithms. So in particular, for instance, this is like a result for the dynamic regret on the path-length setting. So for this, you can actually see we draw two figures that basically we draw the average regret one that basically along like the T iteration. So basically want to make sure the regret that actually you can see there are some like shifts, but basically it is converging to 0. And maybe I think this is like a better figure to show like the asymptotic behavior that basically we compute this regret over like a square root of T times the path length P and also this log term here. So this is basically the asymptotic bound that we are given in our paper, and we conduct this in our we conduct numerical experiments for this. So basically, you can see that if you really like we consider this kind of ratio, there are some really oscillations along this, but basically it is actually always upper bounded, which suggests that actually this is at least like an upper bound about like what is happening about our prediction of the online prediction of the quantum state. And similarly, we also conduct numerical experiments for the adaptive setting. And for adaptive setting, I think this is really a figure that I like. I think for the K-shift setting that we also construct this kind of symptotic bound. You see, like for a different setting of the experiments, everything really converges to roughly speaking like 0.03 here. So this really suggests that probably our theoretical prediction is good. In like a symptotic sense, and also the average regret is here converging to 0. So these are like some demonstrations about like our dynamic and adaptive regret results. And I think for this, finally, I think we really want to have a good understanding about like what skills in terms of dimension, because like the dimension of the number of qubits of the quantum state, along this task of learning is probably typically the most difficult thing that we want to deal with. So I think, unfortunately, because I have to say that our numerical simulation is conducted on classical computers, so we cannot handle like really large, a large number of qubits. But we have conducted our experiments, for instance, like we consider like the K-shift setting, and also like the number of qubits can be like, for instance, like 6 qubits. I think along this, basically, our quantum algorithm still outperforms the previous classical state of the art. So basically, you can see that the red shadow region is basically our result. So I think looking at this, I think we have like a consistent improvement compared to a previous algorithm. So I think we have confidence that in general, our algorithm is going to perform well for predicting the state online, even like the states are changing. Okay, I think maybe this is another time that I can like make a pause here and collect some questions.
So I have a question. So this result is
Sure,
using QTIP, right? So is the simulation result using the QTIP or other?
Yes, we use QTIP. I guess for this results, I guess in general, we need to think about how we want to generalize the corresponding quantum state. There are some randomness along this line, and actually a QTIP is actually one thing that we use the package to actually generalize the state. And after that, I think we have basically we use Python, and actually we code our quantum algorithm into that, and actually align with the package, and we run this and also like the code for the previous algorithm, and we make a direct comparison.
Okay, yeah, gotcha.
I actually get another question.
Sure.
Could you go back to the like OMD algorithm page? I'm just
I guess maybe this one.
Yeah. So can you express more about the line 2, like how to achieve like to the end dependence, the advantage?
Oh, you mean how do we get?
Yeah.
How do we get rid of that? Oh, this is a good question. Yeah, I'm not sure if I have good intuitions for that. Well, I think this actually is something coming from quantum information theory. I guess in general, basically making such kind of updates are good as suggested, and we just like use the volume entropy. We test this, and actually in our theory it works well. But yeah, I think maybe probably need to think a little bit more to this somehow. I probably need to better. We probably need to think better why this works well. But actually, I guess from the point of information theory, this is a natural try, and it just works. Yeah, but yeah, maybe there are some deep reasons for that. I probably need to have a better understanding about this.
Yeah, I may ask you for the like the book or some materials. Like
sure, definitely.
Yeah.
Sure, definitely.
Yeah, thank you so much.
So other questions? I think I have maybe about 10 minutes, so I think I don't have too many slides. So maybe let's actually go to the rest of my talk. So I think for the talk of today, I basically talk about this problem of adaptive online learning of quantum states. So in particular, I mean, from like a high level perspective, it's really like we apply the tool of online learning into the research area of quantum computing, that basically this kind of mirror descent and basically all this kind of technology. I mean, using this can actually give good results. Basically, this characterization due to dynamic regret and adaptive regret. But how about the other direction? I mean, this is probably a little bit far from like the topic of this lecture series, but this is more like a direct understanding that whether we can give a quantum speed up in terms of regret for like classical online learning problems. So I'm happy to announce that actually recently I also have good understanding about this, that for a bunch of online learning problems that we can get fast quantum algorithm. I mean, especially for bandits problem, like multi-arm bandits, stochastic linear bandits, and stochastic convex bandits, we can give a good quantum algorithm for that. I think due to the time limitation, maybe let me actually very briefly mention this. So what is the bandit problem? So the bandit is just like something you're going to see in Las Vegas, that you have like a bandit machine. Maybe there are some choice. I mean, it's like apple, orange, banana, and like maybe correspondingly you have the probability like 0.2, you have an apple, and maybe the probability of 0.3, you have orange, like probability of 0.5, you have a banana. And actually, if you have these, your corresponding have rewards. So maybe you have an apple, you are going to get $1, maybe like orange $2, like banana $3. For instance, like a problem like that. So this bandit problem is just like very standard. As you see, like you have some randomness. I mean, this also like a very important, I think this basically like a reinforcement learning problem, that you have this kind of thing, you got to make a decision. Basically, you need to decide which arm you're going to choose from the problem you're going to get a reward. So by arm, I mean probably this is like an arm that you have this probability and have this reward. But maybe another like arm is like maybe the probability is like 0.1, 0.3, 0.6, and you have like a different set of reward. Maybe you for that reward is different. I guess we could basically want to choose like which kind of arm you want to choose. So in the quantum setting is that maybe we want to consider like a direct quantum counterpart like this, because you have the capability, maybe classically you have the capability of making such kind of random variable. You just imagine that you have a quantum oracle that you can prepare such kind of quantum state. And like the regret that we are going to use is that, I mean, after you choose an arm, I mean, you choose it, and basically this gives you like a definition of regret, where the comparison is made to like the regret compare like the difference between the best arm possible and the current like choose of your arm here. And basically, this is like the very easy, like the very standard case of the multi-arm bandit, because you have different arms and you want to choose along that. And there's a similar definition along this called a stochastic linear bandit, where the definition domain can be larger, where you have like maybe you don't have like each time choose like a fixed arm, but in general, maybe the best parameter can be something like theta. Maybe you have like a different weights, I mean like a d-dimensional subspace that you can like actually choose along that. So in general, for the MAB, I mean, for the standard case, the classical, it is shown that the classical, I mean, in terms of number of iterations, the t here is at least square root of t. I mean, basically the tight bound is square root of n times t. But quantumly, we can actually give like polylogarithmic regret bounds. So this is really, I mean, a significant improvement for such kind of online learning problem. And also for stochastic linear bandit, we can also give result that you can basically see that this kind of logarithmic regret things. And the technique is basically called something like called quantum Monte Carlo method, due to based on this kind of amplitude estimation. And maybe let me not get into the technical details, but roughly speaking, why can this works really magically? So it's just like actually it's like something from a statistical learning, and actually in general about like something, for instance, like the Chebyshev inequality. Maybe that is something people are familiar with. So by making like, if you want to if you keep to pull like a specific arm, you are actually going to have, I mean, if you keep have ID samples from a random variable, you're actually going to gradually learn the expectation due to like the Chebyshev inequality. But like the classical concentration rate is basically like 1 over square root of t, whereas quantumly, I mean, due to amplitude estimation, this kind of quadratic speed up, the concentration rate is actually going to be like 1 over t. So if you have like T iterations here, classically, this is basically like sort of if a quantum is basically like O of 1. So this is really something, I mean, this is really rough. I mean, this is probably not even very rigorous, but this is like an intuition of why quantumly we can give like a polylogarithmic regret bound for the MAB. And actually, we can also conduct this to the continuous domain. And for the continuous domain, this is like an even harder problem, but quantumly we can still achieve like a polylogarithmic regret bound for this. Okay, so this is like a very rough guideline about this. I mean, well, we have been talking about like the relationship between online learning and quantum computing, and have been for the talk, it's mainly about adaptive online learning of quantum states, more like using online learning to quantum computing. And like very briefly, I mentioned that we can also use quantum computing to give some fast algorithm for online learning. But I think maybe this is just like not deep enough. I mean, we want to have even deeper thinking. I mean, along the way of using some techniques like some online learning in general, like machine learning tools, towards the understanding of quantum computing, I guess there are really some more interesting things maybe we can think about. So, for instance, I mean, especially like this, we want to talk about for this lecture series, the connections to quantum computer systems. And maybe let me just like very briefly, like a little bit brainstorm here. Maybe for instance, there can be some connection to quantum control theory, maybe like calibration. I think this is probably super important. And also in general, along the way of like NISQ, I mean, near-term quantum algorithms. So maybe for that, maybe for the term in terms of like quantum control theory, I mean, it's just in general, I mean, applications to control theory is also have become like a leading research, like super important in the research of online learning. I think, see, for instance, like the talk rethinking control at the Institute of Advanced Studies by Elon Hazan, and this can you just like search the rethinking control on YouTube, you can just find a talk, which is a fantastic talk that summarizes how people have been applying online learning techniques to understand control theory. So I think for this, actually, as I've been thinking about how to apply quantum algorithm for online learning, and also along this, I think a very important thing is that along control theory, the formulation are typically, I won't say it's unclear, but I guess we want to be careful about how we want to make the formulation of a control theory problem that we want to study. But in any case, I think like recent studies in online learning and all these kind of things can be probably really helpful. And I guess after that, like tools from online learning can very naturally play a good role, for instance, like similar to this work. And I guess it's probably for my own interest, but from like a theoretical understanding, I think it's also quite possible that we can theoretically give some quantum speed up of some control theory problems. And I believe this is also I think I really also very look forward to that. So I think in terms of calibration, I think our work basically suggests that changing state is not an issue for shadow tomography, basically like learning measurement outcomes. And I guess in other words, that basically like we make some this kind of post-processing using this online learning techniques, basically this promises robustness. But I think I really want to have a good understanding like whether this kind of thing really help with calibration in real quantum computer system. Because I think, I mean, I'm really like a theorist, I mean, along this, I mean, basically like a theoretical computer scientist. But I think hopefully this work may be helpful to like the researchers in quantum computer systems, or maybe like even like experimental physicists. I mean, I think probably such kind of online learning tools can be meaningful. I mean, like a pre-processing or maybe post-processing of this kind of data. And hopefully maybe like this work can give you some ideas along this line. And I think maybe finally also very briefly mentioning that NISQ algorithms. So I think our algorithm is mostly designed, I mean, for this online mirror descent and also the multiplicative weight, this kind of algorithm, like maybe they're probably not super available on current quantum computers, but maybe, I mean, there are kind of parameters and we can do gradient descent along this line. But how about like the NISQ counterparts? I mean, we can also consider like a parameterized version of this, and maybe hopefully we can give some good demonstration. And I think one thing that we want to mention is that I think actually just now Henry asked a question about like the numerical experiments. And actually in that numerical experiments, in our adaptive online learning paper, we use QTIP. And actually in another paper of mine, so basically this quantum multi-arm bandit paper, we actually conducted numerical experiments for its quantum speed up with IBM QuISE-NET. So QuizzKit is good that basically actually it has some noise model. So I think I have to say that we didn't conduct a lot of experiments, but for depolarizing noise with like Q2 to the error like 1%, like 1 qubit error like 0.3%. I think these are reasonable parameters. I think among this kind of range, our QM quantum MAB is still better than the classical regret of the MAB. So I guess hopefully like maybe the NIST algorithm can take a role in terms of online learning of quantum states and also corresponding problems. Okay, so I'm really running out of time, so maybe let me make a summary here. So today, I think in my talk, I talk about like our recent online algorithm for learning changing quantum states by measurement. And I think basically for a dynamical model can cover a different scenario. So for instance, like the path length, like the family of dynamical models, like the K-shape setting, etc. And also, I think by the talk here, I really want to hopefully not only like we get the information of my talk, you just live this, and hopefully we can maybe have some way of making further collaborations along this line. And I think basically, we believe that maybe it can have like further connections to like maybe such as quantum control, like calibration, like this algorithm sector. And hopefully this can be this talk can be give you some idea, maybe some thoughts along this line. Okay, thank you all for your attention. If you have any questions, just feel free to ask me here, and also feel free to send me emails. Thank you.
Okay, so any questions from the audience? Yeah, before that, I actually have one question. So for the online learning algorithm, I think it is suitable for the scenario where the noise is changing slowly. So I'm not sure how to think about the slowly, like for example, on the real machine, after we do the calibration, the noise will drastically change at that point after calibration, right? So is that will like drastically affect the algorithm here?
I guess for the noise case, that is basically we characterize this by the dynamical model, I guess. Sorry. Oh, it's basically here. So, I think, yeah, I'm not sure how I would describe, like, I guess this is probably something like going to be intrinsic about like the robustness here. I mean, basically the intuition is that as long as your state, I mean, no matter if your state is changing here, I mean, maybe in the worst case, like the state is really like shifting a lot. I mean, in that case, the path length here is really huge. But if the states are changing like slowly, I mean in terms of t, I mean if it's changing like slower and slower, such that basically this path length is like it actually converges, has an up or down, then basically this can be actually covered by our results that the regret is basically like square root of t times the path length t here.
I see. Okay, got it. Yeah.